Hi everyone. So today I'm presenting on the Cohn's irreducibility criterion. So as you might remember, we talked about the Eisenstein's criterion in class. So here is another criterion that can help us determine whether a polynomial is irreducible. So we start with some relevant definitions. The first definition is about the base b expansion of an integer n. So suppose we choose an integer b greater than 1, then every positive integer can be written uniquely in the form stated here. And the coefficients am minus 1 all the way till a0 is in between 0 and b minus 1. And the leading coefficients am is not 0. And as you might recall, the polynomial ring over Z is the set of all polynomials in variable x with coefficients in integers. And the definition of irreducible elements says that if we have a ring R, which is also an integral domain, and there's an element R in the ring R that is neither 0 nor a unit, then we say R is irreducible whenever R equals to A times B implies either A is a unit or B is a unit. So here's the Cohn's irreducibility criterion. Suppose we have a prime number P and B is greater than or equal to 2 and also an integer. And we write P in terms of the base B expansion of B, where the coefficients is between 0 and B minus 1. Then we have a corresponding polynomial fx with coefficients that appear in the base B expansion of P. And this criterion says that fx is irreducible in the polynomial ring over Z. So this is very interesting because it tells us that if we know a prime number, then we can find a corresponding polynomial that is irreducible. So the base 10 version of this theorem is attributed to the mathematician Arthur Cohn. And the generalization of this theorem to any base is due to 3 other mathematicians. And Ramurti gave a simplified proof of this theorem in 2002. So as an example, we can think about the polynomial x to the 8th plus x to the 7th plus x cubed plus x squared plus 1 and ask whether this is irreducible in the polynomial ring over Z or not. So this might not be obvious at first, but if we plug in 2, then we get 397, which is a prime number. And using Cohn's irreducibility criterion, we know that the polynomial corresponding to this prime number, which is the original polynomial, x to the 8th plus x to the 7th plus x cubed plus x squared plus 1 is irreducible in the polynomial ring over Z. So this criterion is pretty useful. So this criterion tells us something about prime number and irreducible polynomials, but we might wonder about the reverse of this criterion, which asks about what can we know about prime numbers if we have an irreducible polynomial. So there's a conjecture that says if fx is an irreducible polynomial in the polynomial ring over Z with degree greater than 1, and the greatest common divisor of f of 1, f of 2, etc. is 1, then this conjecture states that f of x is a prime number for an infinite number of integers x. So this conjecture tells us something about if we know an irreducible polynomial, then we can find an infinite number of primes, which is pretty interesting. But this conjecture has not been fully proven, and it is still an open problem. But what we do know is that irreducible degree 1 polynomials of the form ax plus b always generate an infinite number of primes by the Dirichlet's theorem, which I think is very interesting. So here's a list of references that I used. Thank you for listening.